The Agenda with Steve Paikin is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.
You wouldn't knowingly eat a credit card, right? Well, tonight we're going to find out why the prevalence of plastic in our food chain means we essentially eat a credit card every week. We'll tell you what that's doing to our bodies. Then we'll find out how learning to feed a colony on Mars may help sustain our food system here on Earth. It's Tuesday, October 11th, and that's next on The Agenda. If you are what you eat, and our food chain increasingly includes plastics, what does that make us? With us now on why that's a real and growing issue for our health, we welcome, in Utrecht, Netherlands, Juliette Legler. She's a professor of toxicology at Utrecht University. In Piscataway, New Jersey, Phoebe Stapleton, assistant professor of pharmacology and toxicology at Rutgers University. And here in our studio, Rick Smith, president of the Canadian Climate Institute and co-author of Slow Death by Rubber Duck, The Secret Danger of Everyday Things, which is a great title for a book. And Rick, it's great to have you back here in our studio. And to our guests in Points Beyond, thank you for joining us as well. I want to read this quote here from Nautilus magazine from last May to get us started here and set up the discussion to come. Sheldon, the graphic, if you would. Microplastics have been found in places as remote as Antarctica and the summit of Mount Everest, in fish guts and in honeybees. Researchers recently found tiny plastic particles in the lungs of surgical patients, the blood of donors, and the placentas of unborn babies. According to one study, people may be eating as much as a credit card's worth of plastic each week. Okay, Rick, get us started here. I'm sure people have seen the pictures on the news, for example, of these huge scows of plastics in the oceans and that kind of thing, a garbage island in the Pacific. But how big is the problem of plastic that's actually too tiny for us even to see?
Well, I mean, it's a huge problem and it's getting worse. And you know, as you point out, I think people have seen news coverage of sea turtles being threatened by the plastic in the oceans, you know, very visible problems. But it turns out when it comes to human health, when it comes to the toxicology of plastics, it's what we can't see that's turning out to be the real problem. So in the last few years, scientists have found that when plastic gets into the environment, it never really breaks down. It just, you know, sunlight will break it into smaller pieces. The action of waves will break it into smaller pieces. It gets down to a microscopic size, and then it starts to circulate in the ecosystem. And guess what? It turns out that it accumulates in us, in our bodies.
Phoebe, follow up on that if you would. And if you can, just sort of take us through a typical day. How do these microplastics actually make their way into our bodies?
Yes, Rick is absolutely right. They get broken down into these smaller and smaller pieces. Those pieces are of the size that can be ingested, whether that's through food products, either things that the animal has eaten prior, or the packaging and the processing of the food, of the water that we drink, both tapped and bottled. It's been found there. And then also in the air. So we can be breathing these particles into our lungs. And the size of those particles really makes an impact on where they go in the lungs and also where they go in our GI system after we ingest them.
Juliette, can I just understand that a little better? Are you saying every time we take a swig of water, for example, out of a plastic bottle, we are ingesting not just the water, but some very, very tiny bits of plastic as well?
Well, there's certainly a very good chance of that. Yes, there have been microplastics found in water and in food. The question is, of course, you know, there's also, you know, could be other things in our water as well, including chemicals or other contaminants. But the question is that harmful to our body? And that's, of course, where our research comes in. You know, once we ingest these plastic particles, where do they go in our body, or are they excreted? And will they cause harm there? And that's something we really don't know very well yet, and something that a lot of research is being undertaken at the moment to figure out.
Those are key questions, but I'm not going to get to those just yet. I want to develop the tension of the narrative a little more, because Rick did an experiment on himself.
Yep.
And I'd like you to give us some of the details around that. Why did you do this, and what did you do?
Well, about 13 years ago, Bruce Laurie and I wrote a book called Slow Death by Rubber Duck, where we tried to get at this notion of chemicals in consumer products. So quite often when people think about pollution, they think about big belching smokestacks, they think about water pollution. It turns out these days that most endocrine disrupting chemicals, hormonally disrupting chemicals, most carcinogenic chemicals that people come in contact with every day come from the consumer products we use every day. So Bruce and I over the years have tested ourselves to see to what extent these chemicals will accumulate in our bodies. And a couple of years ago in the Globe and Mail, I did this with microplastics. So I wanted to see, how easy is it just living your daily life?
So you didn't do anything different or special?
A 6-day experiment. First 2 days, I just lived my life normally. I took a stool sample every day. My wife found this all kind of
charming,
extremely off-putting. But in the last 4 days of the experiment, I actually tried to crank up my level. Anything I ate, I made sure came wrapped in plastic. I only drank bottled water for the last 4 days. I left my food out on the table so that household dust, which is mostly microplastics these days, could accumulate on the food. And what we found is that in the last few days of the experiment, my microplastics levels did increase.
Is that to suggest that if you went in the opposite direction, avoided plastic to the best of your knowledge altogether, you could get the amount of plastics in your system to zero?
Almost certainly you couldn't get it to zero because, I'm just looking around the studio here or any building, most household dust in the corner of a room would be microplastics these days. It's in the air that we breathe. Couldn't get it to zero, but almost certainly you could reduce it if you tried to eliminate as much plastic as possible from your life.
Phoebe, apparently last spring there were 2 studies that came out in the UK and in Netherlands showing microplastics deep inside the lungs of surgical patients, of all things, and in the blood of anonymous donors. Now, how important would you say those studies are for our understanding of microplastics and how they move around?
I think those studies are vitally important. They are the first studies to really identify that they are indeed in human tissues. So scientists have been saying that it's likely for a long time, but these were the studies to really identify that they're there. The one in the human lung patients, especially because it used a special type of microscopy to be able to really visualize these particles and identify what they were. The one in the bloodstream was a little bit different. It used a chemical analysis to be able to identify them, but it was really some of the first early proof, along with the other study that you referenced, looking at human placenta, that these particles really are inside human bodies.
And Juliet, let's circle back to the questions that you were asking earlier, namely the most important one. Do we yet know with any certainty how much damage this is doing to our health?
No, I'm afraid we don't. Good news is that there is a lot of research ongoing to try to figure that out. So certainly here in Europe, the European Commission has invested millions of euros into research into microplastics and human health. And I know that other countries all over the world are following. So researchers like myself and Phoebe and others are looking at, so what happens once these plastic particles get into our lungs and get into our system? Can we study how they affect human cells in different laboratory situations? So moving away from the studies with animals into real human cellular models, looking at how these these plastics are taken up, what shape and size is really important when it comes to uptake of the plastics, and then what are the biological effects involved once we look into these cellular experiments.
And a quick
Studies
follow-up
from
for
our
you,
own
Juliet.
lab. Sorry, go ahead.
Forgive me,
Yeah.
quick follow-up, but is it possible this isn't doing damage to us at all?
It's possible. It's possible that these plastic particles are rather inert. I personally think that from our initial biological studies that we've already seen changes in gene expression, and these in our cells, for example, in the placenta cells that we're testing in the lab, is already an indication that there are biological responses ongoing in the cell. Whether or not those responses will end up in a long-term adverse effect is too early to say. But the first initial evidence, we definitely can see a biological response, which you might consider to be considerable, to be comparable to another kind of small particle, like a soot particle from air pollution.
Rick.
I mean, I think I was going to go where Juliet just mentioned there. That so sure, some of the science around microplastics is recent, but here's two things we know about microplastics, and both of them are disturbing. The first is that the chemicals in plastic, we know a lot about them. We know that they have, in many cases, a carcinogenic effect. We know that they have a hormonally disruptive effect. When they get in our bodies, they mimic estrogen. And so that there's been umpteen studies over decades on the negative biological effects of the chemicals in plastic. The second thing we know that Juliet just mentioned, going right back to the Industrial Revolution, we know that bad things happen when humans breathe in small particles. Lots of studies on women during the Industrial Revolution working in big factories, breathing in fibers in the garment industry. We know what happens when miners breathe in coal particles. We know what happens when miners breathe in asbestos particles.
No good comes from any of this.
Bad things happen in terms of the inflammatory effect. So as Phoebe just mentioned, we now know that these particles are in, likely, the lungs of everybody on Earth. It is, I think, inconceivable that turns out to be good news.
Phoebe, can I get you on that as well? Is it possible that while this stuff gets inside us, it may not do any long-lasting damage to us?
I agree with what Juliet said. It's still, I mean, we're both scientists. It's still kind of early on. So I can say that, as Rick is indicating, there are plastic places that I don't want a plastic particle to be. So what those plastic are doing there, in that what the cellular interactions are, if that's leading to some of the negative toxicological effects, it looks like it likely is from a variety of different ways, both, as Juliet was indicating, through some DNA changes that we're seeing, as Rick is indicating, through some endocrine disruption. I think those are all really good places to start, as well as both the lung inflammation and just overall system inflammation. We know that when particles are places that they shouldn't be, as Rick is indicating, that they're doing things we don't want them to do. And now the question is, what are plastics doing when they are there, and what are the different types of plastics doing? Are those different outcomes?
And let me do a follow-up with you, Phoebe. You studied microplastics in pregnant rats. What did you find?
We did. We studied something even smaller called nanoplastic that we haven't touched on yet during this conversation. And that's a plastic that's about 1,000 times smaller than a microplastic. So this is definitely something that we can't see. Unlike a microplastic, it's barely within the visible range. And what we found when we put these nano-sized plastics into our pregnant rat model, we not only were able to find them in the placenta of the rat mothers, but we were also able to find them in the fetal tissues after a single exposure, and that was into the mother's lungs, and that was 24 hours after exposure. We started to look for them in those fetal tissues, and we ended up finding these plastic particles in the rat brain, liver, heart, kidney, lung, places we definitely don't want them to be.
Can you make, Juliet, any conclusions about what this might mean for pregnant women?
Oh, I'm afraid it's very early days for that, and I certainly don't want to alarm pregnant women at this time. What we are doing in our lab, in our studies, is we're doing large-scale epidemiological studies in which we're recruiting pregnant women in order to get samples from their placenta at delivery, and we'll be able to follow up the health of their kids. And only when we do those kinds of long-term studies will we be able to really be able to say with more certainty that there is indeed a health risk. In the meantime, that of course doesn't mean you can't reduce your plastic exposure as much as possible. And what's really important in all of the projects I'm involved in is that we have government policymakers on board who are thinking about how can we assess the risk of these microplastics. There's such a really complex mixture of contaminants. It's not just one type of dust particle. It's a really complex group of contaminants of many different kinds of plastics, many different kinds of shapes and sizes and colors, full of different kinds of chemicals. So really complex when it comes to the policies we need to make there. But I also would like to say it's really important that we have in some of our research some of the plastic manufacturers on board who are looking for ways to produce better plastics, reduce the use of plastics, better understand how microplastics are formed from their products. And that's all really important work to think about solutions to this huge problem.
We certainly will come back to the issue of solutions and what we can do to change our behavior, change public policy. But before we get there, I want to talk to you, Rick, about the brain. Microplastics in the brain. What have you learned?
Well, I mean, Phoebe's actually done some of this groundbreaking research, and what she has found, and she should wade in here. I don't want to put words in her mouth, but as rat moms breathe in these particles, they then wind up in their fetuses, wind up in the brain compartment of those fetuses before the blood-brain barrier, in that critical moment of development that occurs in mammals, rats and people and others, where blood circulates in the body before that blood-brain barrier solidifies. And so these particles get locked into the brain. So in some of the, Phoebe, you should wade in here, but in some of our discussions, I mean, you've wondered about a link to Alzheimer's as
Phoebe,
one example.
You want to pick up on that, Phoebe?
Sure. There are some concerns. It's that the plastics are places that we didn't think we would find them because of those barriers. I didn't think that they would get past the placental barrier, and I certainly didn't think that we would find them in these tissues. Now, that's not to say that they're directly in competition or directly in some type of, next to a brain cell. They may still be in the vasculature of the brain. And these are some studies that we still have ongoing is exactly where they are, and therefore what they're coming in contact with, and therefore what kind of toxicology there may be. But I do know that we talk about dosage, and the dose of these particles and how many we're finding in the brain is very, very low in comparison to how many we originally put in. But I know they're in an area that we don't want to be finding them as well. So it really begets more what if studies and what we're going to be able to find from finding them there originally. But a lot more work is left to be done if they do have links to some of these neurological conditions that have increased in numbers as time has gone on.
Juliette, I want to quote a colleague of yours. You're going to help me with pronunciation on his last name, Dick Vetak. Is that how he says it?
Yep, very close. Vetak.
Okay, very good. Ecotoxicologist, part of the research team that discovered microplastics in the blood, and he asks the following questions. Where's it going in your body? Can it be eliminated, excreted, or is it retained in certain organs, accumulating, maybe, or is it even able to pass the blood-brain barrier? Okay, today we don't know the answers to these questions you tell us, but how long do you think we're going to have to wait before we will know with certainty how to answer these questions?
Well, not very long, I think. So, as I mentioned, a lot of research ongoing in Europe and around the world. In projects that I'm coordinating, we're looking at human blood-brain barrier models. So we could be able to predict the uptake, but not only of one type of plastic particles, but of many different kinds of plastic particles. In addition, we're looking at uptake through the GI tract, through the placenta. So there's a lot of research ongoing. I think in the next 5 years, we are going to have a lot of answers to these really, really important questions.
In the meantime, Rick, the standard pushback against people who are making the argument that you are making, for example, is that, number one, we don't know with certainty today that this is doing any harm to people or their offspring. Number two, the burden of proof ought to be on you that it is in fact doing some damage. What's your response to that?
I mean, let's just reflect on the bonkers thing about this debate, which is that we're having a calm discussion here today about the fact that humans are suffused with tiny plastic particles, that babies are being born pre-polluted. I mean, there was a study just in the last couple of weeks showing plastic particles in a human breast milk. I mean, it's inconceivable. And so the notion that the plastic industry advances, that none of us should be terribly concerned because there aren't any bodies in the streets that can be pinned on plastics pollution, is nonsensical. So for starters, 40% of all the plastics produced are for single-use items. Plastic straws, plastic cup lids, crummy plastic packaging on vegetables in the grocery store, stuff that could easily be eliminated. So rather than the onus being on consumers, being on governments to wait for the evidence to take any action, we need to reverse that. And we need to start asking, wait a minute. How do we start reducing the amount of plastic in the environment? How do we start reducing the amount of plastic in you and me and our kids? Okay, while we're also trying to pin down some of these scientific questions, but the lack of certainty is not an excuse for inaction. The lack of certainty should be a driver of concern and an immediate regulatory and corporate action.
Are you having these conversations with people in the plastics industry these days?
There's lots of conversations going on. Unfortunately, here in Canada, I mean, Juliette is in Europe, where European governments are moving much more aggressively than North American governments. Here in Canada, the federal government, to its credit, is trying to get rid of a few, like a half dozen disposable plastic items that can be easily replaced by other materials.
Well, straws are pretty much gone now, aren't they?
Getting there. But the plastics industry is actually taking the federal government to court. The government of Alberta is actually taking the federal government to court. And I have a very hard time believing that Canadians would find those reasonable actions. I mean, yeah.
Let me find out from Juliette. What's happening in Europe on this front, Juliette?
Well, in Europe at the moment, there's a regulation ongoing that should be passed soon to completely restrict the use of intentional microplastic use in cosmetic products. So at least the first step is being taken to reduce and restrict the use of these plastics that are used intentionally. And what also is going on is that chemical industry is involved in research, developing their own projects and working together with academic partners to work towards better replacement, better recycling, and looking at which plastics are really the worst when it comes to potential human health effects. And those are the ones to start with.
Phoebe, let me read this from Albert Rizzo, who's the American Lung Association's chief medical officer, who compared microplastics to the effort to convince governments that maybe they ought to cut down on or try to convince people not to smoke. Same kind of campaign. And Albert Rizzo says, by the time we got enough evidence to lead to policy change, the cat was out of the bag. I can see plastics being the same thing. Will we find out in 40 years that microplastics in the lungs led to premature aging of the lung or to emphysema? We don't know that. In the meantime, can we make plastics safer? Okay, that's the question for you, Phoebe. Can they make plastics safer in the meantime?
I think it's exactly what Rick was identifying, that there's this back and forth of we haven't found something, so we're not understanding what it is we're making them safer for. And I think in the plastics industry, there's been a lot of cat and mouse. For example, there are many products that are now BPA free, and that's great. But the chemical companies have transitioned BPA to some other chemicals instead. Those same plastics, instead of BPA, might have a BPF or a BPS in them. So they're just changing the chemical construct of something that we knew was unsafe. And that's concerning because it is this cat and mouse game. So instead of that greater good understanding of is it something that we can transition, make some changes to, I think they would argue that they don't know what they're changing for or what they're changing against because those toxicological studies aren't firm. As Rick said, there aren't bodies in the ground that can be directly related to plastics.
Well, okay, Rick, let me do this follow-up. Even at a certain point, the smoking industry understood that it was dealing with a harmful product.
Took a long time.
Took a long time. If you ask people in the oil and gas sector today, they will acknowledge that they're contributing to climate change. And, we can argue about how much time we've got to deal with that. Are there people in the plastics manufacturing business today that acknowledge this is happening and something needs doing?
Yeah. In my day job, I work at the Canadian Climate Institute, so I think a lot about the difference in the trajectory of these different pollution issues, right? And with climate change, yes, there's lots of challenges. Yes, there's lots of work to do, but the oil and gas industry is at the point, by and large, of buying into the concept of net zero. By 2050, we got to eliminate greenhouse gas emissions. There's broad consensus on that. We are nowhere near that point when it comes to this plastics debate. If the plastics industry gets its way, we're going to see a doubling of plastic production by 2040. And here's a crazy statistic. The acceleration of plastic production and use has been so rapid, even in the last 10 years, that half of all plastic made and consumed in human history has occurred in the last 15 years or so. And the plastics industry harbors the ambition of doubling that again over the next decade. So the first thing we need to do with this plastics question, if we want to get it out of our bodies, protect our kids, is start cutting back on the unnecessary use of plastic. There's lots of good uses of plastic, things that make our lives better. Probably half of the plastic produced goes into things that could easily be made out of other things.
In which case, is it ultimately up to consumers to lead a charge on this?
We're starting to see this already. I mean, there's a triangular relationship between consumer preference and consumer pressure, regulatory action by governments, and then the response of companies. And we're already seeing with chemicals, Phoebe mentioned BPA, phthalates, some of these other plasticizing chemicals. Young parents especially know to look for these when they shop. So we're starting to see manufacturers respond, and what we need to see is improved regulatory action quickly.
I'm going to ask our director for a 3-shot so I can say thank you to all 3 of my guests. There's Rick Smith on the left, President, Canadian Climate Institute. Phoebe Stapleton in the middle from Piscataway, New Jersey. She's professor at Rutgers University. And Juliet Legler, professor of toxicology at Utrecht University, who came to us from the Netherlands tonight. My thanks to all 3 of you for joining us here on TVO. Much appreciated.
Thanks so much.
Thank you.
Thanks for having us.
If humans want to go where no one has gone before, and yes, that's a Star Trek reference, they'll need to solve the problem of food. They won't be able to bring everything they need from here, and they'll have to find a way to source it out there. However, that ingenuity could end up also helping us back here. A new book examines all that. It's called Dinner on Mars, the technologies that will feed the red planet and transform agriculture on Earth. And with us now for more, the co-authors of said book in Rome, Italy, Lenore Newman, director of the Food and Agriculture Institute at the University of the Fraser Valley, where she's a Canada Research Chair in Food Security and Environment. And in Guelph, Ontario, Evan Fraser, director of the Aral Food Institute and a professor of geography at the University of Guelph. And we are delighted to welcome you two back to our airwaves tonight here on TVO. Lenore, get us started. How did the pandemic help create this book in the first place?
Yes, it is kind of strange that this book came out of being trapped in a very small enclosed space, much as if one was on a trip to Mars. Although I didn't expect the pandemic to actually last as long as a trip to Mars. But when Evan and I were stuck when the pandemic unfolded, as most of us were, we started chatting about, well, I guess we can't go to this research site or this research site. We might as well be on Mars. And the idea came up then, well, what would we eat if we were there?
And Evan, your response to her asking that question was what?
Well, it was such a silly conversation at first, right? But I mean, everyone was bored and didn't have any toilet paper, or we all had our toilet paper in our basement. There was none in the stores. And it was that, it was a very fraught moment in the spring of 2020. And my response was, well, let's take it to back to the basic building blocks. Like, could we imagine building a food system on another planet where solar radiation is scarce, where there's hardly any water, where every organic molecule you're going to use needs to be created somehow. And it was it was started as a silly thought experiment, and it morphed into a serious thought experiment that then took form in a book. Yeah, so taking it back to the beginning.
And here we are. Well, let's do a little quote from this originally silly and now serious thought experiment. And here's a quote from your book, Dinner on Mars. As the two of us have gone on this imaginary mission, we have come to believe a Martian community can and will feed itself successfully, and that in doing so, develop technologies that will revolutionize agriculture on Earth. Seem preposterous? We don't think so. In our opinion, figuring out what the first Mars dwellers will eat is a topic that may define the future of how we feed ourselves. This is fascinating because obviously all sorts of people have thought about what colonizing Mars would be about, might look like, but I'm not sure anybody's ever taken the next step to think about how people on Mars would actually feed themselves. So you've done us a service by getting there. Lenore, how did this get on your radar screen in the first place? The notion of that next step, how people are going to feed themselves on the red planet.
Well, I think Evan and I are both kind of odd people in that our actual day job is looking at the terrestrial food system. And also we're both science fiction buffs. And I think we've watched the question of food be kind of waved away a lot in the popular press in space. And of course, existing space missions have always taken takeout with them. Very, very expensive takeout. And when you make that next step to Mars, we realized that is a critical element because it is too far to bring food with you. So you have to build it from scratch there, taking as little as possible along for the trip. And when we started, to be honest, we were not sure we had the technology yet to solve this problem. And I mean, the kind of spoiler alert is we really do think we could do it now, but it took a little bit of intense thought experiment to get there.
Well, let's see how that works, because presumably, I mean, it's not going to happen today, but Evan, take us 50, 60 years down the road. What's the foundation of a Martian-based food system then?
Yeah, so the punchline is the technologies are almost ready, but not quite ready. So this is near future technologies. This isn't Star Trek replicators. And for me, it all starts with the humble cyanobacteria, which is sometimes called blue-green algae. It's the stuff that often grows on a summer's afternoon in Lake Erie and creates these huge algae blooms. And on Earth, it's a response. Plants or lakes get filled with often agricultural runoff, fertilizer off the fields, and the lake's ecosystems go crazy producing cyanobacteria. What I learned in going down one of the many rabbit holes that this book took me down, what I learned is that there's a group of scientists in Germany who have reconstructed what's called Martian regolith, basically the sand of Mars, and they've reconstructed the chemical components of it. We know what it looks like from Martian rovers' works in the past, and they've shown that actually using ingredients only found on Mars, you can grow cyanobacteria. And in doing so, the cyanobacteria helps neutralize a very toxic substance. And I've only ever read it, so so apologies if I'm mispronouncing. It's either percolate or perchlorate. It's a chemical compound that in very small quantities will give lung cancer to humans, and it's all over the Martian sand. So you need the cyanobacteria to do two things. First of all, to turn the basic ingredients that you find on Mars into organic matter, and second, to get rid of or neutralize these percolates or perchlorates. And so I think the basic foundation of a Martian community would be a large stainless steel vat kept warm by solar radiation, probably using some concentrators or some mirrors or some fiber optics to concentrate the sun's energy. Because remember, Mars is quite a bit farther from Earth, so there's less sun's energy out there. Have to shield out the harmful radiation, so you'd probably bury the thing. And you would produce cyanobacteria. And with the organic matter produced by the cyanobacteria, you would then build vertical farms and other sorts of bioreactors to produce proteins. But I think the basic workhorse of a Martian food system would actually be blue-green algae, more properly known as cyanobacteria.
Okay, in which case, Lenore, how complicated would it be to create? I mean, Mars is a pretty inhospitable planet by Earth standards. How hard would it be to create soil where you can grow something?
Well, I think the first thing is I'd probably skip the soil, which is part of my day job as well. And I really think the backbone, the workhorse, once we move up from cyanobacteria, is going to be hydroponic plant systems, to the point that living on Mars will feel very much like being in a garden, in that there'll just be plants everywhere. And that's partly for food, but they'll also play a really critical role in providing base organic material and also recycling oxygen and recycling the water. So anywhere you look, there's going to be a plant, and most of them will probably be useful. And that was one of the big things we came to realize on Mars the plant is going to be king, and it's much harder to keep anything else alive. And the plants will probably do pretty well. And in fact, it would be much easier to populate Mars if we didn't have people. They're kind of the weak point in the whole system, is having to keep these really annoying movable organisms alive. But, I do really like plants. So think of it as building a garden based on algae.
Sounds like you like plants more than people. Is that right?
Some days, definitely.
Some days.
Yes.
Okay,
they're
good
and they're quite a bit more complicated than us. It's one of the weird quirks I love telling my students is corn has a much more complicated genome than people do, and so it might be why the corn is kind of taking over and maybe actually in control.
Gotcha. Okay. Evan, talk to us about nanotechnology and the contribution it can make to creating a functional food system.
Well, I mean, there's a tremendous amount of really interesting things happening at what's called the nanoscale. So that's bigger than molecules, but smaller than anything that humans can sort of interact with. So this would be like the, 1,000th of a hair follicle in sort of size. And a lot of neat stuff happens at the nanoscale. And another of the rabbit holes that this book took me down was conversations with really serious nanotechnologist scientists. And there's really sort of two things, or a number of areas in which nanotechnology can help. First of all, if you create these really, really tiny balls of starch, which actually are naturally occurring in sweet corn, you can put little tiny bits of fertilizer or medicine, and on Earth, actually, the gold standard or the holy grail of this is to put tumor-fighting cancer drugs into these little tiny balls of starch and then key them so they actually get into a tumor or get into a cell of an organism and release either the nutrient or the toxin or whatever you're trying to do. So nanotechnology essentially offers us a way of being orders of magnitude more precise with, say, inputs. If you could use nanotechnology to sort of deposit that molecule of nitrogen into the plant right where it needs it, you'd have virtually no waste. So that's sort of what the nanotechnologists are working on. The other thing is what's called carbon nanotubes, which would be these 1 atom thick tubes of carbon where the sides of the tube are 1 atom thick. And these are incredibly strong, incredibly flexible, and are increasingly being used on Earth for all sorts of crazy applications. Apparently they were even, you can find carbon nanotubes in Damascus steel swords from the Middle Ages. So there was some very, very sophisticated smithing going on 1,000 years ago in Saudi Arabia and whatnot. But at any rate, these nanotubes can be used for all sorts of materials. And so between a delivery mechanism and really, really strong flexible materials, the whole wild world of nanotechnology offers us tremendous opportunities, I think, if we're trying to do something in as inhospitable an environment as build a community on another planet.
And Lenore, do I infer correctly that this hydroponic plant system, which is going to be the basis of the food system on Mars, that system will produce the majority of the food that people on Mars will eat, however many years down the road?
Basically, in a nutshell, yes. There'll be kind of 2 main tracks where we get the cyanobacteria. We'll do 2 main things with it. One is produce plants. And of course, we like those. So fruits and vegetables, that'll be quite easy to take care of. Protein, though, is going to be a bit of a trick in that here on Earth, of course, the majority of protein is still animal-based, and we know it's really inefficient. And even on a planet as lush as ours, we are having trouble producing animal protein for everyone without causing serious environmental damage. On Mars, it's just impossible. Animals are too inefficient to take part in that. It would you wouldn't be able to create enough protein. So protein on Mars might be plant-based, but it will also more likely be fermentation-based or grown in the lab. And a lot of people have probably heard about breakthroughs on lab-grown meat and sort of wonder, well, that sounds pretty Star Trek. It can't be that close to development. But the reality is it is pretty close to development. And Evan and I actually got to go down to San Francisco and try some salmon that have been grown in the lab. And it's almost Mars ready. So I think that'll be one of the sort of surprises to us is it will be a system where everyone's eating a plant-based diet, but they won't really entirely notice because the meat will be there. It'll just come from the lab or through fermentation. The one trick and the thing that I think we are still thinking will be a real struggle is here on Earth, we really do rely heavily on carbs, almost to excess, because they're really easy to grow. On Mars, carbs are going to be kind of expensive. So spaghetti might actually be a bit of a treat meal in a Martian community because we just won't be able to grow carbs the way we do here. They take too much space.
So, well, you're in Rome right now, so I got to ask this question. No pasta? No pasta in Mars?
Well, there's going to have to be some, or the Italian astronauts will not cope without their pasta. It's a very carb-heavy diet here, so definitely there will have to be some carbs, but they'll actually be somewhat more expensive in terms of energy to create than some of the other foods, and that's kind of backwards to the way it works on Earth.
Mm-hmm. Okay, Evan, cheese. Will there be cheese on Mars?
Yeah, well, I mean, we're going to go back to that conversation or that comment Lenore just made about fermentation. And, humans have been fermenters for almost all of our history. Some would argue all of our civilized history, and maybe civilized history starts with fermentation. But in all seriousness, we have utilized microorganisms, often yeasts, but not always yeast. Sometimes it's a fungi, sometimes it's a bacteria, to turn some sort of starch into something that we care about, like alcohol. We do this on all sorts of things. Kimchi would be a great example of a vegetable ferment. And now we've been using what's called precision fermentation in labs and in our food system for about 30 years here on Earth. So the first big breakthrough was in the 1990s when the world's insulin supply for diabetics shifted from animal-based insulin to fermented insulin. And basically what happened there is that scientists bioengineered a microorganism to produce insulin instead of producing, alcohol or carbon dioxide or other normal things that fermentation does. Another big breakthrough was in the early 2000s when scientists engineered a microorganism to produce rennet, which is the enzyme that produces cheese or used to curdle cheese. So at that point, about 20 years ago, most of the world's rennet shifted from animal-based rennet to fermentation-based rennet. Well, there's companies springing up all over the world right now who are using microorganisms to ferment all sorts of proteins. And another of the products that Lenore and I sampled for this book was what came out from a company in San Francisco called Perfect Day that has a microorganism that produces whey protein. So this is exactly the same protein as cows produce, except it comes out of a microorganism. It doesn't come out of a cow. And they're producing ice cream and cream cheese, a couple other products. And they're great. They are fabulously good quality products. So our hypothesis is on Mars is that, yes, there will be cheese, but it will come from a fermentation-based protein as opposed to an animal-based protein.
But it sounds like, Lenore, you're both saying it will be a lot easier if the Martians of the future are vegans. Fair to say?
I think they will be simply for energetics reasons. And I actually feel that will trickle back to Earth in a lot of ways. And we're already seeing that. We're seeing a rise in plant-based diets globally now. I mean, there's some ups and downs in local markets, especially in North America. But we are seeing more substitute protein products here on Earth. I think on Mars it's a given. And because these products will be identical, no one's really going to miss the bad environmental outcomes of animal agriculture or the animal cruelty element. And I think philosophically it'll be very interesting to see how that develops on a different planet. But I do agree with Evan. This isn't going to be a civilization of people with no bad habits. They will definitely have alcohol.
Yeah. Okay. Huh. How are they going to are they going to be able to create it on Mars, alcohol?
So if you can produce starches quite easily, potato, for instance, you could grow potatoes, you could synthesize sugars in a number of different ways, and then ferment it. So I think vodka-like drinks will be quite common. There might be a little bit of barley grown around a Martian, a domed Martian crater with a bit of a lake in it. One can imagine, a little fanciful, but what the hell? Maybe there's a Martian bourbon in the future or something like that. But certainly a potato-based ferment would doesn't stretch the imagination. And that's practically what Matt Damon did in the movie The Martian. I mean, he didn't make the booze, but he was growing the potatoes.
So you're not going to be able to call it Grey Goose. You're going to have to call it Red Goose or something like that, given it's the red planet.
Red Goose, yes, for sure.
Yeah. Someone was laughing about Space Side instead of Space Side whiskeys. Anyhow.
Lots you can play with there.
Lots of fodder for puns.
Well, tell me this: if the food system is going to be completely different, will there be garbage on Mars in the future? Lenore.
I think we'll see very little waste on Mars. Anything that can be recycled will be recycled, and we'll really see tight closed loops because we're putting so much energy in at the front end to create that cyanobacteria and then build it up into a system. And those technologies will be exported right back to Earth because we need those today.
Well, that gets to my next point, Evan, which is this started as a fun thought exercise, but presumably some of the things you learned in the course of writing this book could be very helpful to averting food crises here on Earth today, such as, for example.
Yeah, so this is where it gets deadly serious, and the joking drops away, and the goofiness of this thought experiment vanishes. And I think there's two things that I'm going to take away from writing this book with Lenore that are directly applicable to Earth. And the first is not the technologies, but the mindset of incredible efficiency, the mindset of figuring out how to use the waste products of one part of the system as inputs into the other. So the waste product of the cyanobacteria tank becomes the inputs for the vertical farm to produce the vegetables. And it's that mindset of incredible efficiency and closed loops that we desperately need here on Earth. And if I have one hope for this book at all, it's that it communicates that sense, not of the wonder of the technology, but that sense of needing to be more efficient and develop closed loop systems here on Earth. So that's the first thing that I really think that this becomes deadly serious. The second thing that becomes really serious is that while Lenore and I got excited about the technology, this is not a technotopian technology will save us. The technologies we're describing are amazing, but they're not panaceas, and they need to be backed up with really smart, good policy and economic incentives to use the technologies right. So, for example, if one of the benefits of producing all this food on essentially no land on Earth is that we could maybe imagine freeing land up for nature if we don't need as much farmland, that extra farmland that doesn't get needed, isn't needed anymore. Well, that has to be protected. You can't just turn that into an Amazon fulfillment center or a subdivision. You actually have to protect it. And people that are currently on that land need to be compensated for what's happening. And so there's a whole lot of policy implications and societal questions that come out that are really, really serious. And I think doing the thought experiment of Mars helps point us in the way of thinking of some of those solutions.
In which case, let's consider the state of our global food system today, and we're going to do that by starting with a comment here from The Guardian from last month. Here's the quote. Across the drought-ravaged Horn of Africa, 22 million are at risk of starvation. Almost a third of Pakistan is underwater, and as much as 4/5 of its livestock have died. In southern China, drought and a heat wave are putting crops at risk. These follow Russia's invasion of Ukraine, which affected supplies from two major exporters and sent energy and fertilizer prices soaring. That's from The Guardian. Okay, we had you two on just, I guess, shortly after Russia's invasion of Ukraine to discuss the global food crisis. And at the time, the executive director of the United Nations World Food Program said, quote, Ukraine has only compounded a catastrophe on top of a catastrophe. Okay, Lenore, start us off. How would you characterize where things are today?
I think we're in a bit of a paradox right now because a lot of the immediate term news we're getting is very bad. But on the flip side, we are rapidly developing the technology to take the global food system and create an intensive local food system that will produce food using technology year-round, anywhere, anytime. And we're seeing both of these things happen at once. Where we're seeing hunger spreading around the world, we're also seeing farmland being returned to wilderness because it's simply not needed anymore. And they're both happening on the same planet. And basically, it's a bit of a race between chaos and technology. And I'm an optimist, so I have to feel that technology might win, but it's a near thing. And we need to really lean in heavily to moving toward that advanced food system as fast as possible. Even if we don't go to Mars in the near term, we need it here.
Evan, according to the United Nations, world food prices fell for the 6th straight month in September. How much is that helping to ease the crisis?
Yes, the last few months are sort of what's happened since we chatted back. I think it was April, Steve. There was this terrible situation. The grain barges and the grain ships from the Ukraine were not able to get out into world markets. And I think I said at the time, we better hope that the Canadian farmers and the Canadian prairies have a really good summer, because we're really going to depend on what comes out of North America this year. And luckily, we threw the dice and Mother Nature cooperated with us, and the farmers stepped up, and Canada has actually had a bumper harvest. There's never been more wheat in the Canadian prairies than this year. So that, plus the grain ships moving out of blockade in Ukraine, a drop in international energy prices, which has helped bring food prices down, has taken the sort of the roll off the boil a little bit, in the last couple of months, and that is helping. And we are still in this sort of chronic crisis situation, if you can be in a chronic crisis, where we're right at the edge of what many people can tolerate. And people, because of high food prices all over the world, hundreds of millions of them are slipping from very poor to abject poverty. And so it hasn't boiled over like I thought it was going to, partly because of the Canadian prairies just having this outstanding year. But last week, OPEC decided to cut production, and oil prices are going to go up again, are already going up again. Food prices will probably follow. So I don't think that even in the short term we can breathe a sigh of relief. I think we're in a very, very precarious position in the short term. In the medium term, I think Lenore's right. We can move towards a more intensive local system that will provide sort of some longer term solutions. But over the next year, 2 years, maybe 5 years, I think we're going to lurch from crisis to crisis as climate change and civil unrest and trade volatility continue to upend the system we've depended on for the last 50 years.
Do you ever have those moments, though, Lenore, where you scratch your head and you look around the world and you see all of the awful news and devastation that so many other countries are dealing with right now, and yet Canada had a bumper crop this year? You ever scratch your head and say, how is all that possible?
Probably not, but then it's kind of my job to understand how that's possible, I guess. I mean, Canada is in a very lucky position in terms of food. We're a food superpower. To be honest, we should stop subsidizing oil and gas and start subsidizing like broccoli and leafy green production, because we're good at food. We're good at producing carbs. We always have been. We have the land, we have the water, and we also have the technological know-how, and that doesn't get enough play. And we also will probably be one of the first large countries to switch totally to green energy. I mean, we're already quite close compared to many. So in a way, we got lucky. And in another way, we've invested in a lot of these systems. So, I mean, it's good for us, but we also have to remember we're part of a global community. And really, the fact that anyone's hungry at all is a policy failing, not a technological failing.
It's a political decision, I think you've told us in the past.
Exactly. We have chosen to build a world in which some people are hungry and some have more calories than they can ever use. That really reflects poorly on us as a species.
Evan, I want to take you back overseas. And while there is an actual war going on between Putin's Russia and Ukraine, there is also an energy war going on between Russia and parts of Eastern and Western Europe. And I wonder how you see that affecting the price of fertilizer and or other things necessary for what we've been discussing going forward.
Well, starting about in the 1950s, we had a series of technological breakthroughs around developing fertilizers and pesticides, irrigation, tractors, and things like that, that really yoked the food system to the energy system. So ever since the 1950s, the price of food has been way more sensitive to the price of energy than it has been to, say, population growth or whatnot, or demand. So food really reflects the input costs of energy much more than it reflects anything else, or the price of food does. And so So anything that affects the energy market, such as a destroyed pipeline that's supposed to take natural gas from Russia into Germany, is going to directly affect the price of food. And really much of where this is felt is in the price of fertilizer. Fertilizer, specifically nitrogen fertilizer, is extremely energy intensive to produce. Can talk about the technical details, but basically you've got to squish air down under intense pressure and heat it up to a very, very high temperature. That's a very intensive, energy intensive process that requires lots of natural gas. And out of that, you get synthetic nitrogen. So anything that affects the price of natural gas in particular really affects the price of fertilizer. The other thing which is affecting the price of fertilizer, though, is China's demand for fertilizer. And they're buying huge amounts of fertilizer from global markets. So you put those two things together, high energy prices and extreme demand from Asia. And I looked the data up recently, and I think a lot of farmers across the world have seen their input costs rise by 200-300% in the last year or 18 months. So you think of our food prices, a consumer food price inflation is running a bit somewhere between 10 and 20%. Farmers have been facing 100 to 200% input price inflation for things like nitrogen fertilizer. So that really puts a lot of farmers into a really tough situation, and anything that keeps that energy market volatile is going to be problematic. In the longer term, we're going to find alternatives and we'll find more energy efficient ways of dealing with this problem. But in the short term, like this year, next year, there's a heck of a bill to be paid if you're a farmer in the world right now.
We are happy to remind people that for more, both serious and silly ideas, these two have collaborated on Dinner on Mars, the technologies that will feed the red planet and transform agriculture on Earth. Lenore Newman, Evan Fraser, thank you so much, as always, for joining us on TVO.
Thank you.
And that is the agenda for Tuesday, October 11th, 2022. How did Ontario turn a projected $13.5 billion deficit into a $2 billion surplus last year? We'll ask the finance minister tomorrow. I'm Steve Paikin. Thanks for watching TVO, for joining us online at tvo.org, and we'll see you again tomorrow.
The Agenda with Steve Paikin is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.